Welcome back to part two of Unit 4 on analyzing trend lines in scatterplots and residuals. We're going to continue our study of trend lines by learning how to analyze and interpret linear models. We'll also explain the meaning of slope and y-intercept and use something called the correlation coefficient to measure the strength of a linear relationship. When we look at slope and y-intercept, that's probably going to be some review for you from algebra. We're also going to calculate and interpret residuals and then use what are called residual plots to evaluate how well a linear model fits the data. So we're going to take a look at some problems with slope first, and these are just word problems, and they're going to ask us to figure out what the slope represents. So we're given this description here of Surya. This person named Surya gave each member of his family a different playlist of random songs to listen to and asked them to rank each song between 0 and 10. He compared his family's rankings with the release year of each song and created the following scatter plot and a regression line. And it says the fitted line, which is the regression line or the line of best fit, the blue line here, has a slope of negative 0.096. And we want to figure out what is the best interpretation of the slope. So just quick review, the black points are the data points. The blue line is the regression line or the line of best fit. And we have to figure out, what does the slope really mean? Well, before we even look at our answer choices, I'm going to write what our slope is. So our slope is negative 0.096. And that is the rise over the run, which is the change in y over the change in x. And our y values is the score, or the change in the score, divided by our x values, the change in release year. Okay, so if we rewrite negative 0.096 as score over release year, we get negative 0.096 over 1. And so if we say that as a statement, we can say that uh, the score looks like the score is going down by negative 0.096 for every year that is increasing in the release year. So let's see if we can match these up with the answer explanations. So A says a song released in 1950 would have a rating of about 8.75. We'll find 1950 on here. It looks like right here. That looks to be like a true statement, but it doesn't have anything to do with the slope. So we're going to cross out A. For B, it says a song released in 1950 would have a rating of negative 0.096. That's not true at all. That has nothing to do with the song's rating. That's just our slope. C says on average, each 1 year increase in release year was associated with a negative 0.096 point change in score. And it looks like so each 1 year that goes up, I'm just going to put year and score. It looks like every 1 year that goes up on the X, the score goes down by negative 0.096. So C is the correct answer. And then for D, it looks like they just swapped the order. So it says every 1 point increase was associated with a negative 0.096 year change. The years are not going down by negative 0.096. The years are going up by one at a time on the x-axis. So it's not D. D just swapped what C was saying. Okay, let's look at another one. This says Julio distributed a survey to his fellow students, and he was asking them how many hours they spent playing sports in the past day. He also asked them to rate their mood on a scale from 0 to 10, with 10 being the happiest. And he found some data and made a scatter plot with a regression line or uh, predicted values on the blue line here. And it says the fitted line has a y-intercept of 5. What's the best interpretation of this y-intercept? So here's our y-intercept at 5 on the green dot there. And we're just going to go through the answer choices here. Uh, Actually, before we do, the mood rating is on the y-axis and the hours playing sports is on the x-axis. So that's just something to keep in mind. It says for A, the model indicates that students who had a mood rating of 0 will spend approximately 5 hours playing sports. So it says mood rating 0, 5 hours playing sports. That would be here on the graph for A. So it's not A. That would be our x-intercept. Students who had a mood rating of 0 must have spent 5 hours playing sports. Um, so a mood rating of 0 again would be down here, and then 5 hours playing sports. Again, that's also describing our x-intercept. So not B. C says the average mood rating was 5. This isn't telling us our average. We can maybe see the average increase per hour of playing, but it doesn't tell us our absolute average. So it's not C either, which leaves D to be our correct answer choice. But let's go over to see what it says. It says the model indicates that students who spent 0 hours playing sports will have an average mood rating of 5. Um, so this one's gonna be D. And I suppose C would be very close. Um, it's just saying that the average was 5. That would be it's 5 every time, but this is saying 0 hours, mood rating of 5. So that's how we get D. And hopefully that should just be a review for you for these two problems from algebra. If it isn't, that's not a big deal. Just go back and take a look at some of uh, equations in slope-intercept form. Maybe do some quick review on slope if you need to. Next, we're going to look at the correlation coefficient, and I call it the correlational coefficient sometimes. So if you hear me say that way, that's just another way to describe it. But scatter plots let us visualize relationships between these two variables. There's two variables on the x and the y-axis. And sometimes we want to describe the relationship of those variables with one single number. And this is called the correlational coefficient. And it measures the strength and the direction of a linear relationship. And it basically gives us a quick summary of how closely the two variables are related. We call the correlational coefficient R. And it's just a measurement of, again, the strength and direction of a linear relationship. When R is positive, the variables tend to increase together. When R is negative, one variable increases and the other one decreases. It's very similar to slope. Um, if R is 1 or if R is -1, we say that it is a strong linear relationship. If R is close to 0, we say it's a weak linear relationship. So if R was 1, all of our data points would fall exactly on our line of best fit. You can sort of think of R as the line of best fit of the scatter plot. So we want to match these. And this is from Khan Academy. You can drag and drop your answers on Khan Academy. I'm going to write our correct answer next to these numbers. So I'm going to cross this out just for the demonstration here. So the first thing I would do when looking at multiple choice to figure out what is R, I would look for, of these four scatter plots, which scatter plot has the closest correlational coefficient to R equals 1. That would be my first step. And so if we look at these data points, R equals 1 is going to give us a positive uh, linear relationship. So we need to decide which one of these is closest to a straight line that's going in the positive direction on our graph if we look at the different data points. And that looks like scatter plot A is the closest to R equals 1. So now we're going to look at our multiple choice answers and to figure out which one of these answers is the closest to 1 on the multiple choice, 0.88. So that one's got to be A. So if we drew a line of best fit, you can see that those data points are the closest to the line of best fit. In fact, let's do that for all of these. For B, I'm just going to do a rough sketch of line of best fit. For C, I'm going to do the best I can to do for C. C is a little bit tougher. And then here's for D. Okay. Now I want to figure out what would be the closest to R equals -1. Let's try to determine that. So R equals -1 means there's going to be a negative slope. And the data points are going to be very close to the line of best fit. The only two options we have is scatter plot B and C. Those have negative slope. And it looks like B is, these points are closer to the line of best fit than C is. So now we're going to look at which one of our answer choices is closest to R equals -1. Well, it looks like -0.79 is closest to R equals -1. So that's going to be B. So now we've got A and B done. Maybe I should check them off instead of cross them out. Just put check marks by them. We finish those. Now we're going to do the same thing, except it looks like we have C and D showing this is negative. So R is a negative value for C, and R is a positive value for D. And we only have one positive and one negative answer choice. So for C, -0.33 has got to be for C, and D has got to be 0.67. So again, when R is equal to 1 or -1, our data points are very, very close, or they should be exactly on the line of best fit if it's R equals 1 or R equals -1. Let's look at one more of these. Do the same type of problem here. It says match the correlation coefficients with the scatter plots shown. So I'm going to draw the lines of best fit for all of these. Let me see here. A looks like it's negative, and some of these are kind of tough when the data points are really spread out. If you're not sure of the line of best fit, you can skip it and maybe save one of the tougher ones for the end if you need to. But here's the line of best fit for B, C, and D, and I just did a very rough sketch. So now let's figure out which one of these is closest to R equals 1. Which of these data points shows that they're increasing and which is closest to the line of best fit? And that looks like scatter plot D is closest to R equals +1. Now we're going to figure out which correlation coefficient is closest to R equals 1. That's 0.89 is D. I'm just going to cross these out. Okay, now we can look at the closest to -1. It looks like we have A and B are both negative, and scatter plot B looks to be like the data points are closer to the line of best fit. So that would be the closest to R equals -1. Now we're going to go back to our answer choices. -0.75 is closest to -1 of the two negative answer choices. And so that's going to be answer choice B. Okay, we'll check off B and D. We've done those. And now we're just going to see what's left over. So A is negative, C is positive. We only have one negative and one positive left over for our answer choices. A is negative, C is positive. So that's all you have to do with the correlational coefficients. All right, next we're going to look at residuals. So regression lines, they help us to make predictions, but those predictions are not always perfect. And a residual measures the difference between the actual value, which are the data points, and the predicted value from the regression line. So in other words, it tells us how far off the prediction was. A positive residual means that the actual value is greater than predicted. And let me Actually, we have that written here. So a positive residual is the actual value is higher than predicted. A negative residual means the actual value is lower than predicted. And then a residual of 0 means the prediction was exactly correct, which means that that one data point that we're examining landed exactly on the line of best fit. And here's our equation for finding the residual. The residual is our actual data point or actual value minus our predicted value. And we write that as y minus y hat. So y hat is our predicted value. And we can sort of think of it as our line of best fit. And we have an equation in terms of y hat down here for a line of best fit. But let's read the example or the description of this first. It says the fuel consortium chairman at the airport recorded the cost per barrel of crude oil and the cost per barrel of jet fuel each week. After plotting his results, the chairman noticed that the relationship between the two variables was fairly linear. So he used the data to calculate the following least squares regression equation, or line of best fit, for predicting the cost in dollars per barrel of jet fuel from the cost in dollars per barrel of crude oil. And it says, what's the residual of a week in which a barrel of crude oil costs $60 and a barrel of jet fuel costs $78? Okay, so we need to figure out first, what is Y and what is X? So it says predicting the cost in dollars per barrel of jet fuel from the cost in dollars per barrel of crude oil. We're going to say that jet fuel is, we're going to say that's Y and crude oil is X. So now that we've identified our given variables, I'm just going to write what they are in terms of the problem that it's asking us to find the values of. So Y is equal to 78 and X is equal to 60. So that would be step one, just to figure out what the variables are. Now we're going to determine the predicted value from the equation of the line of best fit, or the least squares regression equation, which is this equation that it gives us here. Okay, so we have the predicted value is equal to 2 plus 7 over 6 x. And the predicted value is 2 plus 7 over 6. X is 60 in our variables that we've determined. Now we said y was 78. That does not mean y hat is 78. Those are two different variables. So now we're going to write y hat is equal to 2 plus, that's 420 over 6. Y hat is equal to 2 plus 70. And our y hat value is equal to 72. So now we're going to use our equation up here for residuals, which is y minus y hat. So our residual is equal to 78, that was our y value, minus y hat is 72. And that's equal to 6. We get $6 for our final answer there. So now if we look at this as a data point, let's kind of figure out what this actually means here. The data point is 6 units above the line of best fit. We got a residual of positive 6. And so it's above the line of best fit. So the predicted value, let me write this here. The predicted value, we had y was 72 when x was 60. And if we write that as a point, that would be 60, 72. And then the actual value was 78 when x was 60. And so the actual value was 6078. And let me see if I can just do a quick sketch of that. So this is just a very quick sketch here. So our residual, our predicted value is going to be, we'll say this was 6072, and our actual value is 6078. That's our actual data point there. So if we look at it as a residual, you might see sometimes it's drawn like this with an arrow. And so it's uh, six above the predicted line, or six above the line of best fit, 6 units above. All right, let's try one more of these. This next one's a little bit of a different format. It actually shows us our residual here on the graph. It says Zhang creates and sells wreaths on her website. She gives the diameter in inches and weight in pounds of each wreath. An approximate least squares regression line was used to predict the weight from a given diameter. And it says interpret the residual for the wreath indicated in the scatter plot above. So it wants us to just be looking at this data point here. So the weight is in terms of is the y variable, and the diameter in inches is the x variable. So it says interpret the residual. Before even looking at these answer choices, I would just say, well, it looks like this actual value of the red point is at 8 pounds. And when the diameter was 36 inches. But the predicted value would be that if the wreath was 36 inches, the weight would be 10 pounds. So just from looking at this without any of the answer choices, I would say that the actual value is 2 pounds less than the predicted value. Now let's take a look at our answer choices. It says this wreath weighs 2 more pounds than the predicted based on the diameter. Now this wreath weighs 2 less pounds, not A. B says the wreath weighs 2 fewer pounds than the predicted based on the diameter. That's correct. Now let's just check C and D just to make sure that those aren't correct. C says the wreath has a diameter of 2 inches greater than predicted based on the weight. Well, the diameter isn't bigger, the weight is less, so not C. And it says the wreath has a diameter of 2 inches less than predicted. Again, our diameter is still 36. We have less of a weight. So we're going to cross out D. All right. So that's two different ways of looking at, two different ways of calculating and interpreting residuals. Residual plots are next on our list here. Residual plots are just another way of displaying the same information from a scatter plot and its regression line. So instead of graphing the original y values, it graphs the residual for each data point. And this allows us to see which points were predicted well and which ones were predicted poorly. So let's take a look at these answer choices here. So we try to find residuals that vary from the line of best fit the most. I would say maybe start there. That way you can determine uh, where you're seeing the most variation. And this data point specifically looks like that it varies the most out of all the other data points from the line of best fit. So it looks like it's the most. So when x equals 4, uh, the actual data is at y equals 2. But the predicted data for when x equals 4 is looks like y is 2.6. So that is the actual value the actual value is 0.6 less than the predicted value. Now let's take a look at our residual plot and see if we can find um, something that shows that, where it's 0.6 less than the predicted. So if we look at our x-axis is our line of best fit for all of these. So that's that blue line that I'm drawing right now is the same blue line that we see on our graph here. So we're looking for a data point that's 0.6 below the blue line. And so far I'm seeing A and C for when x equals 4. I'm just going to use the red to match this red point here. So that's 0.6 below our predicted value. Let's take a look at some other values now. It looks like when x is 4 for answer choice B, by the way, it's 0.6 units above. And so we can cross out B. That's not correct. But let's take a look at uh, another data point here. I'm just going to choose this data point, and you can choose any data point that you want, really. But I'm going to choose this one as our next one at where x equals 5, because it looks like where x equals 5, our actual data point falls either exactly on the line of best fit or very, very close. So for A, it looks like that matches up. Oops, deleted the blue line there. So for A, looks like that matches up where x equals 5. Our actual data point falls right on the residual line. For C, not so much. It looks like it's below. So we could cross out C. And that's how we could determine that this is A, just from two data points. And if you wanted to check some other data points, you certainly could. In fact, let's look at maybe just one more, just to double check everything. So x equals 10. It looks like we're at 0.4, but the predicted value at x equals 10, it looks like the predicted value was about 0.7. So that's about 0.3 less um, for our actual value or our residual of negative 0.3. And that lines up with A also. Okay. Let's do one more of these. Um, this next one has some uh in the answer choices, it has some wording that I'd like to go over because I think that you're going to see a few problems like this in the activities that you work on. But we'll get to that in just a second. So here it shows us a residual plot that was constructed after running the least squares regression set of bivariate numerical data. That just means x comma y. Uh, and it says, what can you conclude from this graph? So before we start, I just want to mention that on a residual graph, if the data point is below the x-axis, then the actual value is less than the line of best fit or the predicted value. And if the data point is above the x-axis, then the actual value is greater than the line of best fit or the predicted value. In fact, let me put that here so you can see that for notes. Okay, so we're going to look at our answer choices now. It says the least squares regression equation underestimates y more often than it overestimates y. So in this here, if we look at our residuals, it looks like they're about balanced in terms of under or overestimating. Um, so we've got about +1 there, -1 there, plus zero point 0.2 here, and And this is not exactly plus 0.2, that's minus 0.2, that's minus point, maybe minus 0.6, but it's about balanced. It's not like all of the data, the actual data is above the regression line or most of it is below. It's about balanced. So A is not correct. We wouldn't say that it's underestimating Y more often than it overestimates Y. B says the prediction errors generally increase as X increases. And it doesn't mean always, it just means for the most part in general. So here in the beginning, it looks like when X is 1, 2, and 3, our actual data points are very close to our regression line. But as we continue, X equals 4, now we've got more variation. X equals 5, even more. X equals 6, it looks like it's starting to go back toward the predicted value. But then when we go to X equals 7, 8, 9, and 10, now we're getting more and more variation. And so these errors are generally increasing. They're becoming more and more. I want to talk about C because um, C, you're going to see some questions that ask you about underestimating or overestimating Y. And I want to make sense of this about what that means. So for C, it says when X equals 10, the least squares regression equation underestimates Y. So you might be thinking, well, that looks like it's true at first glance. This Y value is less than the regression. And it kind of sounds like at first that that's underestimating Y. But that's not true. Let's take a look more closely at the wording of this. So I'm just going to highlight some stuff. The least squares regression equation is in green. In fact, let me make that blue so it's a little easier to see because we did blue last time. The least squares regression equation is this blue line here. And it says it underestimates Y. So if we write that as an inequality, I'm going to say this blue line is less than our Y value, which is this black dot. Actually, let's do that in red because we'll just stay consistent with our color coding throughout this lesson. So this blue line is less than the Y value. That's what C is saying. It says at X equals 10, the least squares regression equation line underestimates Y. So is less than Y. Now, is that true or false? Well, our least squares regression line, if we look at it in terms of residuals, our least squares regression line is at 0. So now we're going to write this 0 is less than, and then our Y value, which is our actual value on the Y, looks like it's about negative 0.8. Now, is that true or false? Is 0 less than negative 0.8? Well, that's false. So it doesn't underestimate Y at X equals 10. The least squares regression equation overestimates Y at X equals 10. So C is, whoops, I need to move the screen there. C is not correct. Okay. So you're going to see some more questions that ask you this about the least squares regression equation underestimating or overestimating Y. And I think it's really helpful if you can write some inequality statements. And eventually you should be able to find a nice pattern that will give you a shortcut after you write a couple of these out.